At dawn on a Saturday in Changsha, the capital of Hunan Province in south-central China, a prepared site with a newly cured concrete foundation slab waits in silence. White and red trucks begin arriving in a line, each carrying what, at first glance, looks like an ordinary shipping container. Measurements officially provided by the company responsible indicate that each of these boxes is 40 feet long, 8 feet wide, and approximately 10 feet tall. 3 cranes move into position. A large crew, coordinated by radio, begins attaching steel cables to the modules. The first module is lifted, rotates slowly through the air, and descends into the exact position where it will remain. It locks into place. One worker tightens the bolts. Another checks the alignment. The second module rises. By dawn the following day, a 10-story residential building is standing, complete with walls, floors, windows, corridors, plumbing, wiring, and air conditioning units, all apparently operational. The company's official stopwatch records 28 hours and 45 minutes between the first lift and the completion of assembly. The company is called Broad Group. The modular system is called the Living Building. And the time-lapse video of the event, recorded in June 2021, was watched by tens of millions of people on television networks around the world. The obvious question hanging in the air is simple. If building a house or an apartment building normally takes months, how can a crew erect 10 stories in little more than a day? The less obvious question, the one almost no one asks, is even more interesting. What, exactly, was built during those hours, and what was merely assembled? Before answering, it is worth emphasizing what this scene appears to contradict. A residential building must do contradictory things at the same time. It must support its own weight for decades. It must withstand wind gusts exceeding 60 miles per hour without swaying excessively. It must thermally insulate the interior against cold winters and hot summers. It must block noise between neighboring units. It must keep out rain, even when storms drive it almost horizontally. It must deliver potable water to the 10th floor. It must carry wastewater downward at a continuous slope. It must conduct electricity without overheating. It must ventilate kitchens and bathrooms without returning stale air to the interior. In engineering terms, a home is a small organism filled with interconnected systems. Building all of that in 24 hours sounds like a promise that should not fit within the laws of physics. And yet it happens. The contradiction is not an illusion. It is real. But it is also not what it appears to be. The path to dismantling this paradox begins with a word that almost no one examines carefully. Build. The verb is ambiguous. If building means manufacturing every component of a structure from scratch, then no Broad Group building was constructed in 28 hours. If building means assembling previously manufactured components on site, then yes, the stopwatch is honest. The question is where the observer begins counting. If the count includes the architectural design of the system, developed over many years, the company's patented B-core steel floor panels, seismic testing, factory production of the modules, transportation of the containers to the site, foundation preparation, municipal approvals, and post-assembly inspections, the schedule stretches across many months. If the count begins only when the first module is lifted, then the mark of 28 hours and 45 minutes is literally true. The Changsha project, therefore, does not defy engineering. It challenges the observer's definition of where construction happens. Watching the building appear in a single day is like seeing the final act of a production that spent far longer rehearsing backstage. The first layer of the explanation lies in the way the project was broken down. A conventional home, whether in Uberaba, Chicago, or Wuhan, is a collection of parts that must be fabricated almost entirely on the construction site. A masonry wall is built one block at a time. A floor slab is cast using timber formwork and wet concrete. A pipe is cut, measured, and connected inside channels opened in the walls. Ceramic flooring is installed only after the walls are already standing. Each stage depends on the one before it. Each crew waits for the previous crew. The construction site becomes a sequential chain of events, and the total project duration is the sum of those events. Chinese modular construction overturns that logic at its foundation. Architects and engineers divide the residence into three-dimensional units, known as modules. Each module is sized for international road transport, with dimensions roughly comparable to those of a standard shipping container. Before leaving the factory, each module already contains finished interior walls, installed windows, applied finishes, concealed wiring, positioned pipes, bonded thermal insulation, and fixed bathroom fixtures. It is not a skeleton. It is practically an entire apartment inside a container. Broad Group's living building system, for example, uses modules with a fold-out wall that opens at the destination to create an additional floor section, producing a column-free space approximately 40 feet long and 16 feet wide. The house stops being a collection of operations and becomes a collection of finished components. A useful comparison helps clarify the difference. Preparing dinner at home is like conventional construction. All the ingredients arrive separately, and the cook completes each stage one after another, under changing conditions, constrained by space, time, and climate. Buying a frozen meal from an industrial kitchen, with sauces separated, side dishes portioned, and heating times specified, is like buying a modular home. The final meal arrives faster because almost all the work happened earlier, in a controlled environment, and the last stage is primarily one of coordination. But a house is not dinner. Every connection between modules must transfer vertical and horizontal loads, prevent rainwater infiltration, provide acoustic and thermal insulation, and allow pipes and electrical cables to connect. The comparison is therefore useful as an image, but it underestimates the technical challenge presented by the joints, a challenge that still needs to be examined carefully. The second layer is the factory that replaces the construction site. Broad Group's main facilities are located in Changsha and occupy vast industrial areas. Inside them, stainless steel sheets are cut to millimeter-level precision by digitally controlled plasma or laser cutting machines. Components are welded on jigs that ensure consistent alignment. The company's B-Core floor panels are manufactured on a dedicated production line. They consist of two stainless steel sheets, separated by hundreds of internal stainless steel tubes, welded together to form a three-dimensional truss. The company claims these panels are approximately 10 times lighter and 100 times stronger than equivalent reinforced concrete slabs, and that they can be produced with material waste below 1%, compared with typical waste rates of 10% to 15% on conventional construction sites. According to a McKinsey report published after a technical visit to the company in 2016, approximately 90% of the work on a Broad building takes place inside the factory, in a climate-controlled environment unaffected by rain or wind. As a result, only 10% of the total work reaches the construction site. That inverted equation explains the apparent magic. It is not simply that assembly is fast. Manufacturing has already happened. But the factory is not an automated paradise. A design error reproduced at scale can compromise dozens of units before anyone notices. A minor deviation in the dimensional tolerance of a connection can create a gap of only a few millimeters, yet still prevent proper alignment at the destination. A problem with a batch of stainless steel can stop an entire production line. Industrial precision increases average quality, but it also raises the cost of failure. A mason can build one wall incorrectly and correct the next one, But an engineer who designs a faulty jig can compromise an entire block of identical modules. The third layer, the most important, is the one that almost never appears in accelerated videos. It is the concept of parallel time. While a worker in Changsha installs electrical conduits inside the wall of a module intended for the future building's third floor, another worker, in the same factory or a neighboring facility, installs double-glazed windows in a different module intended for the seventh floor. At the same time, 125 miles away, a civil engineering crew excavates the foundation, assembles the steel reinforcement, and pours a raft foundation that must cure for weeks before receiving the building's weight. Meanwhile, drivers and dispatchers plan the truck route, verify bridge clearances, calculate the width of access streets, and obtain permits for oversized loads. A painter applies an interior finish inside one module. A welder works inside another. An engineer at a digital workstation reviews the design documentation for the bracing system. Each of these clocks runs simultaneously. None waits for another to finish. A conventional project, by contrast, has hundreds of clocks running in sequence, one after another. 200 sequential days become dozens of parallel days. The Chinese modular house has not defeated time. It has defeated the sequential order of construction. Replacing sequence with simultaneity is one of the quietest and most powerful achievements of modern industrial engineering. The fourth layer concerns something that is rarely filmed properly, because it is not visually dramatic: the joints. A stack of shipping containers is not a building. It becomes a building. When the contact points between one module and the next can transfer loads from the top down to the foundation without sliding, separating, or concentrating dangerous stresses at isolated corners. Broad Group's system, for example, uses bolted connections with steel plates, designed so that the four corners of neighboring modules meet at reinforced points, and the building behaves as a single three-dimensional block after assembly. The projects claim seismic resistance against earthquakes measuring magnitude 9 on the Richter scale, as well as resistance to winds associated with Chinese typhoons. That claim was one of the original motivations behind the founding of Broad Sustainable Building in 2009. Entrepreneur Zhang Yue, already known for manufacturing industrial air conditioning systems, decided to create a company dedicated to modular buildings after the Sichuan earthquake of 2008, when tens of thousands of deaths were attributed to the collapse of conventional reinforced concrete structures. The promise of modular structural steel was precisely to resist where conventional concrete construction had failed. The joints also handle other invisible functions. They must prevent rainwater from penetrating the perimeter between modules. They must avoid thermal bridges, points where heat or cold passes through the wall without encountering insulation. They must block the transmission of noise between units. They must allow electrical wiring, plumbing, ventilation ducts, and gas lines to continue uninterrupted. Each of these connections is completed after lifting, usually by specialized crews working alternating shifts during and after assembly. That is why the time-lapse video ends where it does, even though the actual project continues for several more days. Water tightness tests, utility connections, electrical inspections, mechanical system commissioning, and adjustments to doors and windows all occur after the 28-hour stopwatch has stopped. It is worth opening a historical parenthesis here because the industrialization of housing is not a Chinese invention. It began much earlier, in very different contexts. In 1908, the American retail company Sears, Roebuck and Company launched its Modern Homes catalog, offering pre-cut house kits delivered by rail, with every component numbered and accompanied by an assembly manual. Between 1908 and 1940, Sears sold approximately 70,000 residential kits across the United States. After the Second World War, The Levittown development on Long Island refined the model by dividing construction into 26 standardized stages and completing homes at a rate of 1 every 16 minutes during peak production. In post-war Europe, architects such as Jean Prouvé in France and Konrad Wachsmann in Germany developed modular systems to address the housing shortage. In 1967, Israeli-Canadian architect Moshe Safdie designed Habitat 67 in Montreal, using 158 concrete modules stacked in a sculptural arrangement. Post-war Japan developed a powerful industrialized housing sector that remains active today, led by companies such as Sekisui House and Toyota Home, which can deliver residences with almost their entire structural framework manufactured under factory conditions. China, therefore, did not invent prefabrication. It brought the technique to a scale compatible with its heavy industry, its rapid urbanization, and its capacity to mobilize labor and logistics. The fifth layer reveals something that rarely appears on camera. Logistics. A project scheduled for completion in 28 hours depends on a rigid choreography. The modules must leave the factory in the exact order in which they will be installed. The 10th floor module cannot arrive first. The 5th floor corner module cannot become trapped behind the 6th floor central module. A minor sequencing error in the dispatch yard can stop the entire project for hours. Trucks travel in timed convoys, often with police escorts on sections where the loads exceed standard dimensions. Oversized load permits must be negotiated weeks in advance. Cranes with the required lifting capacity, which, for the living building system, must handle modules weighing approximately 30 tons each, are positioned at predetermined locations on the site. A wind gust exceeding 30 miles per hour can force crews to suspend lifting operations for safety reasons. A component damaged during transport can delay the entire assembly. The faster the process, the less tolerance it has for unexpected problems. The fragility of the choreography is the hidden counterpart of speed. A conventional house is slow because it forgives many mistakes. A modular house is fast because it does not. None of this, however, makes modular construction a universal solution. Volumetric modules with shipping container dimensions face physical transportation limits. Many urban streets cannot accommodate a 65-foot vehicle carrying 40 tons. Irregular architectural forms, with organic floor plans or curved facades, are difficult to repeat on an industrial production line. A layout change requested by the client after manufacturing begins can interrupt production and increase costs disproportionately. Local regulations are not always prepared for these systems. Mortgage financing in many countries requires inspections at intermediate construction stages, which conflicts with a project that moves from the factory to the site almost fully completed. Cultural acceptance also varies. Buyers in some regions associate industrial modules with temporary or low-quality construction, even when the engineering is superior to conventional methods. The long-term durability of the joints, real-world acoustic performance, fire resistance during severe fires, and thermal performance in extremely hot or cold climates are still being studied in occupied buildings, not merely in manufacturers' reports. The broad group case also has limitations that promotional videos tend to conceal. The ambitious Sky City project, planned for Changsha at a height of 2,749 feet, taller than Dubai's Burj Khalifa, was announced in 2012 with a 7-month construction schedule, later reduced to 3 months. It never received final regulatory approval. The site where it was supposed to rise became an artificial fish pond. The company also erected a 57-story building in 19 days in 2015, an impressive achievement widely reported by the global media, although its long-term performance under continuous occupation received far less attention. In January 2024, the company completed the 26-story Jindu Tower in 5 days of on-site assembly, using the 16th generation of its Holon system. Each generation refines the joints, exterior cladding, and thermal performance. In October 2025, Broad exported its modules to the United Arab Emirates, and Xinhua reported that the company planned to install Holon buildings in Ohio, Texas, and California. The technology has moved beyond being a Chinese curiosity and become an export product. Now, return to the opening scene. The site in Changsha, the white and red trucks, the 3 cranes, the stainless steel modules descending in an orderly sequence. By nightfall, the 10-story building is enclosed and clad, with windows installed and its internal systems nearly complete. The stopwatch reads 28 hours and 45 minutes, and the scene is real. But the observer now understands that this scene is the final step in a production that began far earlier, probably months earlier, when digital engineers designed every bolt, factory workers cut the first sheets of steel, drivers planned the truck routes, and construction crews poured the foundation that still needed time to cure. The work did not disappear. It simply changed addresses. Modern engineering learned that time, when divided among parallel clocks, moves far faster than when it runs in sequence. The house that appears in 24 hours is not an accelerated house. It is a house built in advance. Engineering did not eliminate time. It learned how to hide it, divide it, and make it work in parallel. The house that appears from nowhere is only the final act of a much longer performance. If you want to keep uncovering the secrets behind the structures that shape our world, click the subscribe button now. Turn on notifications and join us for the next story.